And okay, you're recording. So keep going with the soil description. Oh, just a minute. One student asked me to enter in the class. Okay. So, okay. Okay. So in the last class, we discussed about some topics about soil description, like color and redoxymorphic features, like iron and manganese concretions, piezoplates, pyrite concentration and depletion, and how they change the soil color and what they mean. They mean that soil, they has a lot of influence of water in soil genesis. The process of soil formation, it's quite influenced by water, okay? So keep going with the soil description. Today we will need to describe some topics that's quite easier than soil color, and one of them is boundary, the boundary between horizons, okay? When we are in a field and we have to describe the soil profile, we have to describe each horizon or layer, and we have to describe the boundary between the horizons and or layers. And we always describe the boundary between a upper horizon and the bottom horizon. Okay, always. We don't describe the boundary between a bottom horizon and a subsurface horizon in this example, and this surface horizon, this purple horizon, just always going down the description. Always we have to describe the upper horizon and the boundary with the bottom horizon, okay? In the boundary between the horizons and layers, we should describe according to topics. One of them is distinctness, and distinctness is the change from one horizon into the other horizon. It's the thickness that we can measure, the change in the grading from one horizon, this purple one, to the yellow one. And how fast can I see that this horizon changed to this yellow one? It's very fast. They change in a very few centimeters, or they change across large centimeter, like 50 centimeters, 20 centimeters. I can see a change that course very fast in a thin section or in a large section of the soil. This changing, if they are very abrupt or they are diffuse, they express this soil genesis. If I have abrupt or very abrupt changes, distinctness, boundaries, it's because the soil, it's an incipient soil. I have some properties they doesn't are well defined, they're well developed in that horizon. It's very common to see this kind of boundaries in fluvial soils, in soils that are influenced by river, marine terraces, and influence of colluvium, sedimentation, because these horizons or layers are just be there for a long, for a few time, like just 1 decade or less than 1 decade, just 1 month, 1 season. They are very incipient there. They just being deposited there. And gradual and diffuse boundaries are boundaries that we can see in well-developed soils, like oxysols, ferrosols, or ultisols, soils that are very developed and very bioturbated by ants, roots, and several other organisms. So I can see the distinctness of these boundaries, the changing of one horizon into another horizon, and I can see how this change and understand that this transitional thickness, transitional zone thickness express the soil genesis and express how this material was defined, was deposited, was changed by organisms and the other soil formation factors. In general, materials that are deposited very, very soon, just a few weeks or months or even some years, they present this kind of boundaries. And very old and well-developed materials, they present this kind of boundaries, okay? The very abrupt boundary is defined by a zone transitional that's very, very thick. It's less than 0.5 centimeters. So I can see a changing from this yellow or orange horizon to this gray horizon. The changing, it's very, very thin. I can see very easily this changing, and this zone, it's very, very thin. I don't have a large zone that has a mix of gray colors and orange colors at the same time. I just can see abrupt, very abrupt changing, okay? And I can see this one, it's abruptly changing, that this transitional zone, they has a thickness between 0.5 and the less than 2 centimeters. So I can see a changing from this horizon into this. So I have this sandy material with roots, and it doesn't have a lot of pads, but I can see here a very distinct horizon with prismatic pads with a lot of clay, very different from the upper horizon, okay? This is a clear transitional when we have a zone. We have a zone with a mix of some properties from the upper horizon and the bottom horizon. Like here, I can see very, very easily here an horizon that's brown, has a dark color, and I can see here a yellow one, a brown, and here we have a transitional zone that's very, very thick, okay? I can change and make some another zones like here, like the changing from here to here, the changing from here to here, okay? Here we have a gradual zone, a gradual diffusion, a gradual transitional between a horizon and another horizon. And the thickness of this transitional zone varies between 5 and less than 15 centimeters, like this. I can see this horizon. I can see something like here. and I can see something like here, and I can see that some transitional horizon like here, and I can see that this material has a reddish color, and this is a brown reddish color, and here we have a transitional between this and that. So we have a transitional zone. Oh, I'm sorry. And here we have a diffuse zone, that we have this horizon here, and we can define one another here, and one here, and we have large zones of transitional like this and that. Oh, just a minute, someone asked me something. Okay. Yes, yes, I start to use the pencil to get better. Thank you, Kenneth. Just a moment. Okay. Okay. So we can see some transitional zones like here and here, the changing of this brown and reddish color from just this has a zone that's thick. It's more than 15 centimeters. So we define that we have a diffuse transitional. Okay. And we have the topography. The topography is the lateral undulation of the material. Like we can have this move that we don't have undulations. We have a planar and parallel surface boundary. Like we can see this is the soil surface, and here we have a transitional zone that's parallel, it's planar from this superficial zone, okay? We don't have any undulation here, so it's smooth. We have wavy topography, a wavy transitional, when the width it's it's higher than the depth. So the depth of undulation it's lower than the width, okay? And we can see some variations. That's this one, the irregular. The irregular, we have a higher depth than the width, okay? So with width, it's less, it's below the depth in an irregular boundary. And we can see a broken transitional here. When we have some discrete materials, when we have some fragments of materials here, from this horizon inside this purple horizon. And we can see some spots of this purple horizon inside this yellow one. So we have some pieces, some spots, some discrete bodies of one horizon inside another horizon. Okay. Oh, just a moment. Someone asked me to enter in the class. Okay. Just a moment. Okay. This move topography it's very common. It's the majority of boundaries that we can see in Word. It's very common in 1+1 clay minerals like kaolinite, halloysite. We can see in goethite material, hematite materials. The majority of soils has this kind of transitional, this kind of boundary, this kind of topography. Okay, it's very, very common. We can see this kind of transitional, the wavy transitional, the wave boundary, when we have 2+1 materials. So we have elite, kaolinite, smectite, we have elite, some materials that's very expensive materials, soils that are not so wafered and leached. Okay, so we have some materials that can suffer shrink and swell, and this shrink and swell process, they change the topography of the horizons and they produce a wavy topography. Okay, we can see too irregular transitional in materials that has 2+1 minerals, like in the wave ones. But here we can also see this kind of topography in sandy materials. That's a lot of sandy, okay, like podzols. They always present this kind of material because some clay just eluviate from this material, or organic matter just eluviate and produce these stones that we can see. Okay, and the broken transitional, the broken boundary, it's very common to identify between a sea horizon or a sea layer and the LR layer. So when we are seeing soil and okay, this is the sea horizon, and we can find the R layer, and we can see some pieces of rock here, or we can see some pieces of soil inside, some fragments of rock. Okay, here we can see a broken topography. Okay, oh, just a moment. Someone asked me to enter in the class. Okay. Oh. Okay. So we have all these topographs that we have to describe to understand how soil was formed in this area. And only the topography already says a lot of information to us, because we can see some topographies like this or this, and understand that this material are not so well weathered, so well leached, and not a deeply weathered soil. Okay, probably we can see a lot of materials that are depositing in this material, and the soils are very young and less leached than this one. Okay, here we can see a planar transitional, oh, I'm sorry, a planar transitional here, and I can draw this line, and this line, it's parallel to this line, that's the surface of soil. Okay, the soil surface here, and the transitional line and the transitional zone is here. So here I can see a smooth transition between this horizon, this black one, and this yellow one. Okay? It's very common, as I said. And here we have a like a party. We can see this, and whoa, here and here and here again and here again. We can see a lot of undulations, but this one and this one and this one are a depth that's lower than the width. So the width is higher than the depth, and these are wavy transitionals, wavy topographies. And this one is an irregular transitional, because the depth is higher than the width. Okay? Oh, this one is very beautiful. We can see a transitional here with the stones. Okay, and then another one, and the last one. These are the irregular transitionals. We can see depths that are very high, are higher than the width of the undulation. So here we can see the irregular transitional, irregular boundaries, okay, between this sandy, this white and sandy horizon, and this yellow and sandy horizon. This is a E horizon, and this is a B horizon, okay? And we can also see some spots here. Oh, these are discrete pieces of this horizon, are pieces of an E horizon. So we have some discrete pieces of one horizon inside into another horizon, and these are the broken transition, the broken boundary between a horizon and another horizon. Okay, so I can see in this picture two kinds of transitional, two types of transitionals. A broken transitional between this discrete piece of an E horizon and this yellow horizon, the B horizon. And I can see a regular horizon, a regular transitional, a irregular boundary between this sandy, this yellow, this white and sandy horizon and this yellow one, okay? Here I can see another picture with a broken transitional, like here. Oh, it's very interesting. I can see a piece of rock inside a dark yellow material, a dark yellow horizon, and they are inside this, yellow, this light yellow horizon here. So I have one horizon like P horizon, and inside this horizon I have two other horizons, like this one, this dark yellow, and this one that's a rock fragment thing. I think that's a rock fragment. So just to remember, we have the boundary that we have to describe the transitional zone between one horizon and another horizon, and we have to describe the distinctness and topography. Okay? We also should describe the depth of the horizons. So we have to describe when a horizon or a layer starts and when it ends. So in this picture, I have some horizons, okay? Here I have an O horizon. Here I have an A horizon, a B, and a C horizon. I'm showing you a tape with some measurements. So I ask you all that take some minutes to note which is the end and the start of each horizon. Okay? And we have a big problem here. So how can we solve this problem? Measuring the start and the end of the horizon. Okay? Please take 5 minutes trying to take some notes. How can we identify the beginning and the end of each horizon? Please write in your notebook, and after the 5 minutes, you can type in a chat. Okay? I'm waiting for your answer. Okay. Thank you, Nadima. And Kenneth, maybe you can change, insert the numbers. Okay, the numbers help us a lot. I'll show you again the screen. Okay. Um, okay, let's start. I will start here. Let's start to make the measurements here. Okay. When we are describing mineral horizons like this one, when the organic horizon, it's not so thick, it's not so expressive, we just need to put the tape in the beginning of the first mineral surface horizon. Okay, so we just need to take the type here in the beginning of the mineral horizon, the A horizon, and we need to start to measure all these horizons. So the A horizon, they starts in the 0 centimeter and ends in the 20 centimeter. Okay, this is the A horizon. The B horizon, it starts at 20 centimeter and ends like a big problem here. We can see that it ends here like 13 centimeters, but we also can see the B horizon here like 65 centimeters, something like that. So we can see a changing here, and we can see a changing here, but we also can see a changing here in the majority of the transitional zone. So we should say that B horizon, it starts at 20 centimeter and finishes at 50 centimeter. Here starts here, it ends here, but we have a zone that we have a mix of depths. So we can just insert this information. 13, 6, 5, something like that. Seems 6 to 5 here. This is not, it's not 60. I'm sorry. A and B. A, it's something like this, and B, it's something like this. 30 here and here. It's just 65. So 13, 65 centimeters. Every time that we have a wavy, irregular, or broken boundaries, we have to insert this kind of information. We have to insert that we have some depths that change in the soil profile, okay? So every time that I stop this information, this note, I always know that represents a wavy, oh, I'm sorry, it's a wavy transitional, or irregular transitional, or a broken transition. It's just one of these three. I'm not sure why, which one, but I can just see the description and okay, it's a wavy or irregular or broken transition. It's not a problem. But every time that I saw this kind of note, I always know that we have one of these three transitions, okay? And the C transitional, they starts at fifth and ends in 80, but I need to put this note, the symbol of plus, because I stop it to dig here. So I don't know what is here. I can find rock, I can find another sea horizon, I can also find a buried material or a B buried horizon. I can see a lot of materials below this sea horizon, but I don't know what can I find this in this soil profile, specifically in this soil profile, because I didn't dig below 80 centimeters. So I just need to input this information. Okay, I have 80 centimeters, and I need to insert the symbol that indicates that I stop at to dig in this depth, and I don't know what can I find below. I really don't know. Okay, JJ, so I can see the A horizon depth, the B horizon depth, and the C horizon, but in the O depth, where or how can we measure the depth of the O horizon in this soil profile? As we have a mineral soil profile and the O is not so thick, like, okay, if I can use a tape or a ruler and this has just 5 centimeters, I can use this note 5/0 centimeter. I use a number here, that's the upper part, and it's a positive number, and it ends at the surface, at soil surface, and it ends at 0. So some of our classmates answered that O horizon, the ends at 0, but I should take a note about the start, when the O horizon starts. So the start, for example, at 5 and it ends at 0 centimeter. The A horizon starts at 0 and ends at 20 centimeter. The B horizon starts at 20 and it ends at 50 centimeter, but I have a irregular transitional or irregular boundary here, and here I saw the sea horizon that starts at 50 centimeter and I stop it to dig in 18 centimeters, and I don't know what can I find below this depth. Okay. Here's the same example. Okay. And here is another example when I saw organic soil, when I have a O or H horizon that's very thick, it's very expressive horizon or layer. So I put my tape in the beginning of the organic material, the organic horizon or the organic layer. So I start here, 0 to 10 centimeters. In the A horizon, they start at 10 and finish at 35 centimeters, something like that. And below, the same information. I follow the same instructions below here. Okay, and here you can see I finish again with a plus notation to indicate that I stop it to dig here. So I always put my tape, I start to count the organic layer or organic horizon if I have organic soil. If I have a O or H horizon that's very thick, that has more than 10, equal or more than 10 centimeters. So I has a expressive horizon or layer that should be noted in my information about depth of soil profile. Okay? So it's very important to understand that mineral and organic soils, they should have different notes, different notation according to presence or absence of organic horizons or layers. Another soil property that's very important. To me, it's one of the most important soil properties that should describe it is the structure. The structure is the organization of primary particles. Who are the primary particles? Sand, silt, and clay. They three all are the primary particles. And these primary particles, they used to be together forming pads or aggregates. So these materials are analyzed to describe the soil structure. So I have to understand how sand, silt, and clay are organized as pads or aggregates to describe the soil structure. Okay? I only use the organization of these materials. So if I describe a soil that has a lot of sandy particles, and the sandy particles are covered by a thin material, clayey material, and this material are together. I can see it in this way, and I should describe the structure. I will describe the type of this pad, the shape of this pad. Oh, these are prismatic or a columnar aggregate or a granular pad, something like that. I need to describe the shape of this material. I have to describe the size of this material. So, okay, this has like 2 meters or 20 or 200 millimeters. I should describe the size of this material. And I have to describe the grade, how much these materials are together and how much the primary particles are losing in that soil horizon. I can describe sand, silt, and clay separated in that horizon, or they are all are together forming pads. If I have a lot of pads, I have a strong grade. If I don't have a lot of pads, I have a weak grade. Okay, let's see. This is the types of structures that we can describe. So I have the granular structure, like this one. We have circular pads with irregular surfaces, okay? We have some blocky materials that can be defined by angular materials and subangular materials. We can see some lenticular materials. We can see some platy materials. They all are materials that has a horizontal distribution, but the lenticular, we can see that the distribution of material is not homogeneous. So I have a concentration of material here, and this aggregate is thinner in the opposite sides, okay? When a platy structure, when can see a platy material, they are very homogeneous materials. Like they present this kind of description, and the lenticular, they present this kind of description. They has a difference of the size of the aggregates according to the position. We have some wedges that has a V shape. There are some materials like this, V-shape pads. We have some prismatic pads that are vertically elongated materials, and columnar pads that also are vertically elongated materials, but for columnar they have a rounded base, okay, a rounded top of these materials, different from this that's very angular material. And we have some structures that actually represent an absence of structure, like single grains and massive, because we don't have pads, we don't have aggregates, we don't have the organization of primary particles. Here we just have sand, silt, and clay, but they are not together. They are just by itself. They are not forming aggregates. Okay? And here we just can see an aggregation because this material, it's a cohesive material. They don't present any kind of voids or cracks that start to formate a pad, to formate an aggregate. We can see some granular structures like here, and here, and here. So we can see some materials, some bodies that has a curved and irregular faces, like this. You can see some curves and irregular faces. So this material is described as a granular structure. The granular structure is very common in soils and horizons that has a lot of organic matter. So the surface horizons generally they present a granular structure, at least these that has a lot of organic matter. Like if I found some A horizon or O horizon or H horizon, they generally present a granular structure. Pads or aggregates that has a curved shape, and generally irregular faces. Okay, something like that. They generally also are rich in iron oxides. So in soils that has a lot of soil organic matter, goethite and hematite, I can find this kind of structure. Okay, if you find a soil that doesn't have a lot of soil organic matter, or the content of iron oxides is low, maybe you can't find this kind of structure because it is formed by high intensity of organisms, high bioturbation. And the bioturbation, it increases the soil organic matter content. And when we can find a lot of bioturbation, generally we can see in wet and tropical conditions. Wet and tropical conditions are conditions, it's a climate that helps a lot, that favors weathering and leaching. So it's common to find wet and tropical soils that has a lot of bioturbation and a lot of input of soil organic matter, and a lot of, or a deeply weathering and leaching stage that helps to increase the content of iron oxides. And you all know that iron oxides, iron oxides, they present positive charges, and the organic matter, they present negative charges. So the positive and the negative, they are getting together, and these particles are always together. And they generally are together and creates a curved shape, and they present a curved shape of this structure. And I can see something like this curved shape of pads, of aggregates, formed by interaction between soil organic matter and iron oxides. Okay? Oh, here it's a very good picture that we can see some of them. You can see here, here, here. Oh, it's a very curved shape here. They remember ourselves like some balloons or balls like this. Curved shapes and irregular faces. Okay, a granular structure. We also can describe an angular block structure if I have planar faces and sharp angles. That, as we can see here, can see very easily sharp angles. You can see here sharp angles of these materials. Here, oh, here, you can see always materials that has this kind of description. They present sharp angles and generally planar faces. Faces can be touched by another pad, okay? This kind of structure is very common in 2x1 materials like elite, smectite, and another minerals, because these minerals, they suffer shrink and swell process. They shrink and swell process, produce cracks that create voids and create this kind of structure, something like this. Think that I have a soil here, and we start the shrink and swell process. So the material start to contract. Oh, I'm sorry. Let me start again here. Okay, here. So I start to form some cracks, like here, and here, and some cracks in this position too. And in the dry season, these cracks, they increase, they get thicker, and these materials are just individualized. And now I can see here a pad, here another pad, here another pad, like this. This shrink and swell process, they produce some cracks, and these cracks, they individualized these pads, these materials. Here, we don't see a lot of bioturbation or organic influence in the formation of the pads or information of the aggregates. It's just a physical chemical process, okay? It is very common in soils that are not so wet-fed, not so wet-fed or leached. So we can find here in some semi-arid soils and some desert soils that present this kind of structure. Here it's quite beautiful. In my hand, you can see here, 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 and here. You can see a cubic shape with sharp angles and planar faces, okay? We also can see a subangular block that has planar and sub-rounded faces, like this one. I don't have a circle shape. I present a shape like this, and I can't see sharp angles. I don't have sharp angles. I just see materials like this and this, very irregular materials. And these kind of pads are very common in materials that I have one by one minerals, like kaolinite, but I also can find some oxides like goethite, hematite, and another one, okay? Here we can see a lot of shrink and swell, but they suffer to these process, but it's not so intense, it's not so deeply influenced by shrink and swell process, okay? This structure is very, very common in tropical soils like ferrosols, oxisols, sols, another of them present this kind of structure. Some pictures here. Oh, and this one is very beautiful. The prismatic pads. They are vertically elongated bodies that we can see. They are very common in materials that has a lot of 2 by 1 minerals. So we see this kind of structure in soils that it's not deeply weathered. Okay, soils that we can see in semi-arid conditions or arid conditions, and they should present a uniform texture so the shrink and swell process can create some prismatic features like this. The shrink and swell starts to create some cracks, and these cracks just start to create some bodies that has a vertically elongated bodies, materials formed by shrink and swell process. Yes, it's very easy to see some prismatic bodies here, prismatic features, like here, some biggest ones. Okay, oh, see this one, it's a crack here. Oh, this one's very beautiful too. It's very elongated. You can see here, or here, or here, or here. You can see that vertical distance, it's higher than the lateral, the horizontal distance, okay? We also has wedge pads, wedge aggregates that we can see in some soils that has a lot of 2 by 1 minerals. As we can see in the prismatic materials, we can see some horizons that has a lot of V-shaped structures like this, a V-shape structure, okay? These materials, they show us that the soil suffer a lot of shrink and shell process. And the soil, it's always influenced by water that helps to shrink the material and swell the material. And the particles, they are always shrink and shell and producing this kind of aggregate, the pad. We also can see this kind of structure, that's columnar structure, and the columnar are also vertically elongated bodies, like here, but you see a rounded top. So the top is not flat like in prismatic. Oh, I'm sorry. You can see a sharp top in the prismatic structures, but in columnar, you see this kind of material. The top is rounded. Let me try to draw again. This is the prismatic, and this is the columnar. It has a rounded top, like here, around that top, like here, around that top, okay? This is very common, like here, around that top. You can see a vertically elongated pad, but in the top, it's rounded. It's not a flat like this one. It's not flat. They are rounded structure. They are rounded top structure, okay? They are very common in soils that present high sodium content because sodium helps the elevation of clay from an upper horizon to a bottom horizon, and they create this cap, this hat in a prismatic feature, something like this. I can create a white and a blank slide to present this. Just a moment. Like here, you can imagine a horizon here. Okay. So I have an A horizon here, an E horizon here, and a B horizon here. In here, I can see a lot of clay and active clay, so they has a lot of cracks, and they can change the structure and produce some materials like this. And I can see some cracks here. And so I can see some angular blocks, but I also can see a prismatic blocks too, okay? So if, oh, I'm sorry. So if I have a lot of sodium here, this sodium helps to elevation of clay from A horizon and from E horizon to B, because sodium, they act in the dispersion of pads. They destroy pads by the dispersion of particles, of clay particles. So I always see a soil with a lot of sodium, and I always can see a soil that lose clay particles from the upper horizons to the bottom horizons. And the clay migration, the clay elevation from the surface horizon, from the E horizon to a B horizon, creates caps like here, because clay are always being deposited here, and create like a little concave shape in the top of the aggregates. So they create this rounded top, and you can see that flat structure, the flat in the top, but you see a rounded material. So we have a columnar structure. Okay. We also can describe a platy pad, a platy structure. It's a flat and platy-like structure, like this in the picture. They are very common in alluvial fens, in terraces, in marine terraces, in materials that were recently deposited on the surface, so they preserve the structure of the sedimentation. Okay. Oh, like this. This picture is in the Amazon River, and we can see in the soils that are very close to the river that we have a lot of pads. They just present this kind of structure, elongated structure like this. Okay. And we also have some soils or horizons or layers that even don't present pads. They don't present a structure well developed, that are single grains. If I have a single grain structure, it represents that I don't have pads, I don't have aggregates here. I just have sandy silt and clay particles separated by itself. They are not together. They are not forming our pad. They are just by itself, okay? It's very common to identify this kind of structure in sandy materials when you have a lot of sandy, and sandy is not good material for pad formation because the specific surface of sand, it's not high, actually it's very low, and doesn't help the formation of pads, the cementation and flocculation of particles. So if I have a lot of sand in a horizon, I can find this kind of structurally very easily, okay? Because I just can't see any pad. I only see a material that are by itself, are not aggregated, are not cohesive pads, aggregates, okay? They are not together. And we also can see a massive structure when we don't have a pad. We can see a pad too, but we see some materials that has a coherent mass, and this coherent mass are just broken by some cracks, but I can't see any kind of organization. It's not an organization, a primary organization as PED. It's just some materials that start to be broken in smaller pieces. This kind of structure, it's very common to see and CR horizons and layers, because I don't see a well pedogenesis or well process. Process are not well developed in these horizons. So it's quite common to identify a horizon or a layer that doesn't have pad and aggregate and just have the material, but the material is not a loosey material, it's a coherent mass, so it's different from single grain, because I have all the particles together, but these particles, they don't form a specific shape. So I have a massive structure, okay? Is anyone have a question? Anyone? It's okay for everyone? Okay, okay. Good to know that you are understanding. I will stop the class right now because it's a lot of things, and I need that you understand each part of the soil description, and I will share with you this recording, and I will put some exercises. So I ask you all, try to answer the exercise, try to describe the soil, describe the transitional and the color and the structure of these materials. Okay? I will put the exercise in the Google Classroom, and I ask you all trying to answer. Please, Nedima, open your microphone, please.
Okay, JJ, please, how do you differentiate this massive structure from the granular shape?
Oh, okay, okay. It's a very good question. Just let me show you. Just a minute, okay? Here. This massive structure, they don't present an organization. It's just material without any kind of specific shape. So if I put a knife here, or I use my hand trying to catch some soil, I can see very pieces of soil that have different shapes because they are broken according to the knife or my hand or these cracks. They don't have a specific shape, okay? And all the other ones has specific shapes. Like if I saw this one, I have a specific shape, this one, and this one, all of them have specific shapes. And okay, you can just think, how can I differentiate this one from that. This is a curved shape. This is a cubic shape. This is a polyhedral shape like this. Okay. They are this kind of shape. Okay. This is this prismatic shape. A V shape. Are elongated with a curved top. Flat one. And here we don't have a shape. And here we don't have a shape. But this material are a losing material. And here we have a coherent material, a coherent mass. Okay? You understand right now? Okay, okay, good to know, good to know. Oh, so people, please keep listening the recording, keep reading the material, and in Wednesday we will continue our class, and we continue description of the soil. Okay? So see you. Oh, see, Nedima, please, please.
Sorry, is it possible in a particular horizon to get more than one shape? Can
I'm
you hear
sorry.
me? In a particular horizon, is it possible to have more than one shape?
Oh, yes, yes. We have a lot of shapes in a specific horizon. You can see a lot of them. Like, I can show you an example, just a minute. Like here. Oh, in this picture, like here. Oh, you can see here a wedge structure and prismatic structure in the same horizon. Here, you can see a prismatic shape and a angular block shape in the same horizon. Okay, so it's very common to identify more than one shape, more than one type of a pad in the same horizon. So you just need to say, okay, I have here a angular block structure plus a prismatic structure. Okay, it's not a problem. We can see 1, 2, 3 structures in the same horizon. It's not a problem. Okay?
Okay.
Okay.
It's okay now.
Oh, thank you. Thank you. Has anyone more questions? No? Okay, okay. So, thank you very much. We see.
Hello.
Oh, okay.
Hello, JJ.
Oh, thank you. Bye-bye. Have a good night, everyone. Take care. Bye-bye. See you.
JJ, bye bye.
Bye-bye.